want to thank the organizers, Yelena and Sergey, for invitation to talk in this mini course. And this is the last of the three lectures I'm presenting on the clique number. And today I'm going to tell you about the upper bound on the clique number of Paley graphs. So main goal of the lecture is the following. Let's quickly recall that the Paley graph is defined as follows. So consider a finite field FQ, where Q is a prime power. The Paley graph PQ is the graph whose vertex set is FQ. And there's an edge between X and Y precisely when the difference between X and Y is a square in FQ. The clique number of a given graph is the size of the largest complete subgraph of G. In other words, the clique number measures the size of the maximum clique in a graph G. The clique number is an invariant of a graph, and it's denoted by omega of G. And for any graph G, you can ask this question: how big is the clique number? And in particular, when the graph is a Paley graph, it turns out that computing the clique number is a fairly difficult problem, and it's still an open problem to compute, to give a precise formula for the clique number of Paley graphs. So the main goal of today's presentation is to give a complete proof of the following theorem on the clique number of Paley graphs of prime order. So this result I'm about to show you is a breakthrough result from a few years ago. And it is currently the best general upper bound on the size of the clique number when the Paley graph has prime order. Now, what does that mean? That means that the Paley graph is defined over Fp, where P is a prime number. And here's the result. If P is prime, then we have the following upper bound. The clique number of the Paley graph of order P, where P is prime, is at most this bound, which is square root of P over 2 plus 1. So this is a very interesting result, and it's the currently best known upper bound besides the clique number for a general P. Of course, for a specific P, you can use a computer and you can improve this bound. Now, the trivial upper bound is something that we discussed in the very first lecture, is that the clique number of the Paley graph is at most square root of P. That's the trivial upper bound, and this result is an improvement on that by a factor of square root of 2, by a multiplicative improvement, right? Because the number here is square root of P over 2, so it's a square root over 2 multiplicative improvement on the trivial upper bound. And so that's the goal for today's lecture, is to prove this result. And this result was proved by Hanson and Petridis, and their paper was published in the Proceedings of the London Mathematical Society. And here's the reference for the paper. The paper is called Refined Estimates Concerning Some Sets Contained in the Roots of Unity. Today, we're going to talk about a different proof. And this proof is different in the following sense. The original proof by Hanson and Petridis relied on a method called Stepanov's method. So Stepanov's method is a really deep tool in number theory. But today we're going to discuss a different proof, and this proof was devised by Benedetto, Solymosi, and White. And in particular, we're going to present the following theorem and its proof. So let me explain what the theorem is. And at this moment, it's not going to be clear why this theorem is relevant for Paley graphs. And I will explain that in the next slide. So in the next slide, I'll explain why this theorem is so powerful. But let's just, for a moment, look at what the theorem says. The theorem says the following. Let P be a prime. Let A and B be two subsets of Fp of size at least 2, and the following inequality, that the product of the size of A, the size of B, is strictly less than P. Then, if you look at the Cartesian product, A cross B, then that's a subset, of course, of the affine plane. This is a finite plane. And given a subset of the affine plane, you can ask how many directions does it determine? And the theorem says that the number of directions determined by a Cartesian product is at least the size of the Cartesian product. So that is the size of A times the size of B, and then there's a small correction term. The correction term is minus the minimum of the size of A and size of B plus 2. So this is a striking result because it basically shows that Cartesian products have a lot of directions. They determine a lot of directions. And somehow this product being so large, in particular, in general, this is going to be a large number, is really good. It determines a lot of directions. That's what we want. Usually in theory of directions, our goal is to show that a set contains a lot of directions. So that ends up being really helpful. And so here we have a really nice lower bound on the number of directions. So really the paper is about the paper de Benedetto, Solymosi, and White wrote. It's a paper that appeared in Combinatorica. And it's a combinatorics paper that's about how many directions a Cartesian product determines. And that's the lower bound they get. And in our presentation today, we can actually prove this theorem. And this theorem is pretty deep. And so we're going to require a lot of technical tools to prove it. But in case you're not familiar with your directions, or maybe you saw it in the last lecture but forgot it, I wanted to give you briefly the definition of what does it mean, a set of directions. So recall from the last lecture that if U is any subset of the affine plane, AG2Q, so this just means that affine plane of order Q, and let's say that we coordinatize U so that it's consists of pairs AI comma BI. So that means that U consists of n elements. Then the set of directions determined by the set is simply the set consisting of all slopes, basically. And these slopes are BI minus BJ divided by AI minus AJ, where I and J range between 1 and n. So that's an object that you can associate to any set of points, and that set D is called the set of directions determined by the set U. Okay, so now let's go back and explain how we can obtain Hanson-Petridis bound on the size, on the upper bound on the clique number of the Paley graph. Right? So Hanson-Petridis bound is about controlling the size of the clique number for Paley graphs, whereas the theorem by de Benedetto, Solymosi, and White is a theorem about directions. So you may ask, how does this theorem about directions tell us anything about the clique number of the Paley graph? And the amazing thing is that it tells you so much. This theorem here, it tells you a lot about Paley graphs. In fact, much more, not just Paley graphs, but other graphs too. So let me explain how we can use this theorem. So in fact, we're going to prove something more general. So let's say that D is a positive integer divisor of P minus 1. And Z sub D denotes the multiplicative subgroup of size D that is contained in the cyclic group Fp star. Now recall that if A is a set, then A minus A denotes the set of all differences, X minus Y, where X and Y are both in A. And here's a corollary. Suppose A is a subset of a finite field Fp, such that A minus A is in ZD union 0, then we can control the size of A. That in fact, the size of A times the size of A minus 1, this is at most D. So this is a pretty interesting and general result about the structure of the set ZD. So what are we really saying here? Let's think about the definition of ZD. ZD is a multiplicative object in its nature because it's the multiplicative subgroup of size D. And here we're imposing an additive structure. We're saying a minus a, which is certainly an additive structure, is contained in a multiplicative structure. And there's a general principle that says that multiplicative structures cannot really contain much additive structures. So if they contain an additive structure, then that additive structure cannot be too big. That's the intuition. So that means that if you can find a set A that satisfies this condition, then A cannot be too large. And that is quantified by the conclusion. The conclusion says that A cannot be large in a very precise sense. So let's explain the proof of the corollary. Well, the directions determined by the Cartesian product, A cross A, is contained in ZD union with 0, infinity. And why is that? Well, that's because we're assuming that A minus A is in ZD union 0. So if you look at the definition of the set of directions that are determined by a set, you're looking at these pairwise differences because the direction is Bj minus Bi divided by Aj minus Ai. Right? That was the definition of a direction. So if you're assuming that this set is A minus A is inside ZD union 0, that means that when you compute the directions determined by A cross A, then you're gonna land inside this object ZD union 0 and potentially infinity, because you could potentially get vertical direction, right? That's when you have the same x coordinate but different y coordinates. Then you get this vertical direction. But in any case, what does this mean? That means that there's at most d plus 2 directions, because the size of ZD, that's a multiplicative subset of size d. So there's d elements there, and there's 2 elements here. So that means that the number of directions determined by A cross A is at most d plus 2. So that's an upper bound on the number of directions. But the theorem by Benedetto, Solymosi, and White gives a lower bound on the number of directions. So if I apply the theorem, what do we get? We get that the number of directions determined by A times A is at least A times A minus the minimum of A and A, but the minimum of A and A is just A, plus 2. So that's a lower bound, and the upper bound is d plus 2. And if you look at this and cancel out 2 from both sides, you get exactly the desired inequality. So that proves our corollary. And now let's explain why this corollary gives a proof of Hanson-Petridis bound. Well, let's think about it. What should we pick the value of d? We want to pick the value of d so that the multiplicative subgroup of size d represents quadratic residues. And there's only one obvious choice for d. We want d to be p minus 1 over 2. Because if d is p minus 1 over 2, then the set ZD consists exactly of non-zero quadratic residues. Why is this good? Because if A is a clique in the Paley graph, by definition, being a clique in the Paley graph means that if you look at pairwise differences of your elements in A, then those pairwise differences will be perfect squares in FQ. That means that if A is a clique in the Paley graph, then A minus A is inside the set of quadratic residues, union with 0, because you could do x minus x, that gives you 0. But this is great because now I'm satisfying the condition of my corollary. Applying my corollary, I get that size of A times the size of A minus 1 is at most d, but the value of d in this case is p minus 1 over 2. And this gives you an upper bound on A. Notice that A here is the unknown because I'm interested in controlling the size of the clique. And if I just do a basic quadratic formula, then I'm basically going to get that the size of A is at most 1 plus square root of 2p minus 1 over 2. And this is exactly, I mean, this matches the Hanson-Petridis bound of P over root P. P divided by square root of P, I apologize, square root of P divided by square root of 2. That's what this bound gives. So basically, if we can prove the theorem by D. Benedetto, Solymosi, and White on the number of directions determined by Cartesian product, then we obtain this corollary. And this corollary is very strong. You just specialize this corollary in the case when D is P minus 1 over 2, and you just get that the size of any clique in the Paley graph of order P, where P is prime, is at most 1 plus, so basically is at most square root of P over 2. So, and then basically our conclusion is that we need to show this theorem. So that's the key theorem. So let me state again, we need to show that if P is prime, and I take two sets in FP of subsets of size at least 2 with this inequality, then the Cartesian product A equals B determines quite a lot of directions. Now, what does it mean quite a lot? It's the size of A times size of B minus the minimum of the size of A and size of B plus 2. So the rest of the lecture is going to be devoted to proving this theorem. Okay, so we went through this. We already went through the slide. And we're going to move on to some technical details. In the last lecture, I talked about theory of directions, and I introduced Rede polynomials. I'm going to present a quick review. If you have a set of the affine plane, so this is a subset of points, and I've coordinatized the plane, and my points are ai comma bi, and the value of I ranges from 1 up to the cardinality of u. I'm going to let D to denote the set of directions determined by the set U, and we can always change coordinates so that the vertical direction is in D. Now, letting n to be the size of the set I'm interested in, the Rede polynomial of U is defined by the following object. So it's the product I goes from 1 to n, xi plus aiy minus bi. So there's a bit of a small typo here. There's no xi here. So this is just x. So I'm just gonna erase this here and annotate. So there is no subscript here. This is a polynomial of 2 variables, x and y. So it's x plus aiy minus bi. So Rede polynomials are interesting object, and last time I talked about their importance in the theory of directions, and we're going to see that again today. So what is it? It's a way to take a combinatorial object, like a finite set of points, and associate to it a polynomial in 2 variables. And somehow this polynomial encodes a lot of information about the point set, especially information about how many directions the point set has. And we're going to see why. Okay, so given a fixed y in FP, we will often consider the restriction of the Rede polynomial when I just fix the value of y. Well, if I fix the value of y, then we're going to get one variable polynomial in FPX. This is x here. Sorry for the typo. Wait 1 second. Give me a second to. So here, for each fixed, I'm going to clear the annotations so that we're not distracted. So clear all annotations. So for each fixed y, we're going to look at the set ay, and ay denotes the multiset. Minus ay plus bi, I goes from 1 to n. So why do I say multiset? Well, because it is possible in theory that some of these could collide. So given a fixed y, maybe some of the AI y plus bi's, they could be the same. So it's important to keep in mind that, there could be repetitions. And one fact that I proved last time is the following. Is that AY, this set, consists of distinct elements. This consists of distinct elements. If and only if x to the q minus x divides this polynomial hyx, if and only if y is not in the direction set determined by you. So this equivalence is highly, highly useful. We're going to use this again and again. So there are three conditions here. One of them is about a certain set, AY, being consisting of n distinct elements. The other one is about divisibility of the Reday polynomial. So this is the Reday polynomial when you plug in for a fixed y, you plug in the value of y. So you get a polynomial in x only. And this is sort of like an algebraic condition. And then the corresponding geometric condition is that y is not in the direction set. Okay, so let's use these facts.
Shamil, sorry, but
yeah.
Question. What is q?
I'm sorry, say again.
What is q? X to q minus x divides the polynomial. What is q? The last row.
Oh, excellent question. Sorry, this is this q here. So yeah, this doesn't. You're totally right. There's a bit of a typo here. So this q would be p in this case. So this should be p using this notation. But in general, there's nothing special about primes here. So all of this, as I explained in the second lecture, this actually works through over fq, where q is not necessarily prime. So here you can write ag to q, and then here you can write x to the q. Hopefully that answers your question.
Okay, thanks.
Yeah, thanks for pointing that out. So yeah, and these polynomials over fq are nice because we know they split completely. So that's where it comes from. Now I'm going to define certain sets, and these are going to be called sigma k sets. So let me explain the notation. Let's say that y, a fixed choice of y, is not in the direction set. That means that the quotient polynomial has a root at every point of fq minus y. Well, why is that? Because because this should be ay, not y, but ay. This is because x to the q minus x is divisible by hyx. That's exactly this point here. Now, because y is not in D, I know that hyx divided by x to the q minus x is a legitimate polynomial. But not only that, because x to the q minus x has distinct roots, all the roots of x to the q minus x is just all the roots in fq. And then the roots of hyx are roots of ay. The roots of this set hyx is just roots. These guys are the roots. I just basically get that this is a polynomial at every point of fq subtract ay. So let me also just indicate that here in case there's any confusion, whoever's watching it. So I'm just going to indicate that here. So this here, by this I mean you subtract ay. So I'm looking at fq, but then I'm subtracting ay. Because the roots, because the ay is already contained here. So roots of this is already ay, so then you get the rest of the roots. But we know just from basic algebra that if you look at a polynomial which vanishes on a given set, which is fq subtract ay, then again, this you can treat this. This could be p, or this could be q. This should be q. So q and p are interchangeable in this case. I really should be working over fq. Basically, the point is that the theory of directions works fine for fq, but at some point we're gonna switch and use the case when q is prime, because that's when the result holds. So in particular, the roots of this polynomial are symmetric polynomials. They're symmetric in the roots. So of course they're symmetric in the roots, and the roots are simply fq minus ay, where sigma k is a kth elementary symmetric function. But I want to understand what these sets, what does it mean symmetric function? Well, we all know what symmetric functions look like. They're called elementary symmetric functions, but we want to define them on multisets. So there's a bit of a tricky part to this. And the idea is we can actually define these sets recursively. What do I mean by that? So to gain a better understanding of the set sigma k fp minus ay, let's look at the following. Let's look at the following equality. So by definition, sigma k of fp. So this is the case I'm looking at the case at the moment where y is not in the direction set. Now, this is important. If y is not in the direction set, then ay consists of distinct sets, distinct elements. So ay is literally a set. We don't have to worry about multiplicities. We don't have to worry about multisets, nothing. I mean, ay consists of n distinct elements. So of course, fp minus ay is also consists of complementary set. So everything is fine. And for this, we know the definition of elementary symmetric functions. If you think about what the definition of elementary symmetric function is, it's easy to see that to get sigma k fp, because you're taking all possible combinations of the elements in fp, and then you're adding them. So this is just the k symmetric polynomial. Then it's easy to see that you get a representation of this in this form. It's a product over all I going from 0 to k, sigma I ay, and sigma k minus I fp minus ay. And the reason is that every term consists of picking I terms from ay and picking k minus I terms from the complement of ay. But it's an easy exercise to see that if k is between 1 and p minus 1, then this sum is 0. So this is where we use primality, right? This is where we use primality. But this equation that I just wrote down actually gives a recursive way of expressing sigma k fp minus ay in terms of sigma I ay for I less than k. Why is that? Well, because you start running this formula, start with k equals to 1. If you start with k equals to 1, then you get basically the formula for sigma 1. And then you do k equals to 2, then you do k equals to 3. And basically, this formula allows you to express sigma k in terms of sigma i's. And the reason being is that you use the previous, you can use this formula to represent sigma k fp minus ay as some combination of the sigma sub j fp minus ay for j less than k. But then by recursion, by induction, those are expressible as a polynomials in sigma I ay. So what's the punchline? The punchline is that elementary symmetric functions of fp minus ay are actually themselves individually can be expressed as polynomials in sigma I ay. And this is going to be useful because from the recursion, we get that this is a polynomial of degree at most k. Right? We kind of saw it here. Notice that this is a polynomial of degree 2. This is a polynomial of degree 3 in a sigma-wise. So in general, we get that it's a polynomial of degree at most k in y, in the variable y. And the key insight is that this polynomial can be used as the definition of sigma k fpay, even when ai does not consist of distinct elements. So that was kind of the insight behind this calculation, is that first you assume ay has distinct elements, right? That allows you to write down this recursion, and then that allows you to write down polynomial expressions for sigma k fp minus ay. But then you say, okay, well, I have those polynomials, right, already fixed. Let me just remember them. Those polynomials could serve as a definition now of the set sigma k fp minus ay, even when ay does not consist of distinct elements. Okay, so then we so remember, n was the number of elements in our set that we're interested. And we look at m, which is p minus n. And then we consider this polynomial. So what's the significance of this polynomial? So this is another polynomial in 2 variables. And this is a very interesting idea because we basically cooked up a new polynomial now in 2 variables, x and y. What is this new polynomial? Well, it's got degree x to the m. So you see x shows up here. But then you may say, okay, well, where does the y show up? Y should also show up, right? It's a polynomial of x and y. Well, y shows up in these coefficients, sigma 1, sigma 2. There's implicit dependence on y here because we defined sigma k fpay as a polynomial function of y. But let's just remember why sigma k fp minus ay is important. Well, this came from taking the quotient of hxy with fp minus x to the p minus x, right? We did this calculation earlier. So we took the quotient, we looked at x to the p, this should be p, x to the p minus x divided by hyx. So x to the p minus x divided by hyx. We looked at that quotient and we know that the roots are exactly fp minus ay. So that's why if you look at x to the p minus x and divide that by hxy, divide that by the Reday polynomial, you get f of xy. But the catch is this equality is only true for y that is not in D. This is very important. Okay, so let me highlight that. So for all y that is not a direction determined by the set U, we have this equality. This is an interesting equality because both of these are polynomials in x and y, but somehow when you, right, so for y not in D, if you look at this product, then all the terms in x cancel and you just get this. Okay, so here's what we're going to do now. We're going to write down the product of hxy with fxy. So we can just take this product. Now let's not stipulate what y is. So if you fix y to be not in D, then that product simplifies very nicely. But let's just not do that. Let's just treat y as a variable. If I treat y as a variable, then of course, if I multiply hxy with fxy, I will get degree x to the p. Why? Well, because fxy has degree m, and hxy has degree n. And if you multiply them together, you get degree m plus n, which gives me p. And I can write down the rest of the coefficients. And of course, the rest of the coefficients depend on y in this way. So I'm writing the product as a polynomial in x with coefficients depending on y. And of course, that the total degree is P. So the degree of HI has to be at most I for every I. And because we know that hxy times f of xy is x to the p minus x for each y that is not in D, let me just put that extra mark there. That is not in D. Then we see that hy of 0, h sub y is 0 for each y not in D. So let's think about what I'm saying here. So we took the product of capital H with little f. We got this polynomial. And I know that this polynomial, when I specialize for all y that's not in D, that product just becomes x to the p minus x. But if it becomes x to the p minus x, that means that all the middle terms are gone. All the middle terms are 0. And that's the reason why hy is 0 for every y that is not in D, because hy is exactly these middle coefficients. But now, since infinity is also in D by assumption, and we have p plus 1 directions altogether, that means that hy has to be identically 0 for I less than p plus 1 minus D. Okay, so why is that? Well, because remember, hi has degree at most I. This is a degree at most I polynomial. But it vanishes in at least p plus 1 minus D points. So why is that? Because it vanishes for every y that's not in D, and the number of elements that is not in D, the number of directions that's not in D is p plus 1 minus D, because it's the complement. So you have a polynomial that vanishes in p plus 1 minus D points, and it has degree I. Well, if I is less than the number of points it vanishes, then the polynomial has to be identically 0. That's what we're saying here. So in conclusion, if the polynomial is not identically 0, then that means that this inequality should be reversed. So I has to be at least as big as p plus 1 minus D, which rearranges to the direction set being at least as big as p plus 1 minus I. And therefore, what is this observation? This observation shows that if you want to get a good lower bound on the set of directions, then you need to find a high degree term here, high degree term meaning like one of these terms, that's 0. Why? Well, if you can show that a high degree term here vanishes, then that means that hiy is 0 for some low value of A. But if that's the case, then we get a very good lower bound on D. So suppose you have a set A cross B, that's a Cartesian product. Now we're going to use M for the number of elements in A, and we're going to use M for the number of elements in A and N for the number of elements in B. So the notation is a little different now because previously the set had N elements. Now the set altogether has Mn elements. So let's say here's my elements of the set A, and here's the elements of the set B. So, and my goal eventually is to show that the Cartesian product has a lot of directions. Well, let's make a few observations. When M is 1 or N is 1, then the set U is contained in a line. But then in that case, it spans only one direction. Observation 2 is that if C is any subset of AG2P with C at least P plus 1, then C determines all directions. So this is a general fact that if you have more than P plus 1 points, then you determine all directions. Now, why is that? This is from the pigeonhole principle. Because there are P parallel lines in each direction. Now, by the pigeonhole principle, there must be a line in each direction containing at least 2 points from C. That's because I'm assuming that the number of elements in the set is more than P. And there's only P parallel classes, parallel lines in every direction. That means that one line must contain at least 2 points. But then that means that you get that direction. That means that you acquire that direction. So C determines all directions. That's the proof. And because of observation 1 and observation 2, it means that we can always assume that M is at least 2 and N is at least 2, because M equals to 1 and A equals to 1 is not interesting. And then this is also not that interesting, because then you just get all the directions. And well, in this case, my set is a Cartesian product, which has Mn elements. That means if Mn is bigger than or equal to P plus 1, I'm done. There's nothing to do. So therefore, I can assume that Mn is at most P. But P is prime. So Mn at most P is equivalent to assuming that M times N is strictly less than P. So these are going to be our assumptions in the theorem. So we're looking at a Cartesian product of A and B. A has at least 2 elements. A and B has at least 2 elements. And the product of the sets, the product of cardinality of A with the cardinality of B, is less than P. And also, we're going to make a slightly simplifying assumption, which is that we can always translate one of the sets. And that doesn't really do anything. And so we might as well assume that 0 is in B. So it turns out that assumption can help in the proofs. Okay, so let's remember the definition of Reday polynomial. So the Reday polynomial is the product over all elements in the set. And it's a product, in this case, of over all I and j of x plus aiy minus bj. So remember, A is the set consisting of the numbers A1, A2, blah, blah, blah. And B is B1, B2, all the way until B sub M. Or, sorry, I got the M and N wrong. So A is all the elements A1, A2, all the way until AM. And B is B1, B2, B3, all the way until Bn. And as before, I'm going to define the set A sub y to be the set consisting of minus aiy plus bj, where I is between 1 and m, and j is between 1 and n. And for simplicity, let's define fq minus ay, the complement of ay, to be denoted by ay bar. Now, this is the definition that we had earlier. So we define little f of x, y. So this is a polynomial in 2 variables. And it's defined, we already saw the definition of this. And so this is the same definition as before. So it's a polynomial of degree k. And what is k? It's p minus the number of elements in the set. So earlier in the beginning of the talk, it was like p minus n, because n was the number of elements in the set. But in this case, we're considering the Cartesian product, and the set of interest has mn elements. So that's why the degree of f is p, which is the p in fp. So this is the number of elements in the field, minus mn. And by our assumptions, this is a positive integer. So remember, we assumed that mn is less than p. That means p minus mn is a legitimate positive integer. And this polynomial is defined in this way. The coefficients depend on the set. The coefficient depends on the quantity sigma ay bar. And earlier I mentioned how you can define sigma k of the indices are missing here. Sorry about that. This is just sigma 1 and sigma 2. and sigma 3 all the way until sigma k. So these are just the elementary symmetric functions on the set A-wise. Okay. So we're going to consider the Raday polynomial in the horizontal direction. So what does that mean? I'm going to specialize hxy, the Raday polynomial, which is defined here, by setting y equals to 0. Because what happens in this case is that f of x0 times h of x0, when you plug in 0 into y, you just get f of x0, this one, times, well, if you plug in 0 for y, notice that this term, AYI goes away because y is 0. So all you get is x minus bj, and it's repeated m times because the number of elements in the set capital A is m. So there are m choices for each AI. So for each bj, there are m choices for the AIs because it varies through every element of the set A. That's why you're getting this repetition. And when you multiply this, you're just going to get a polynomial in X, right? You're just getting a polynomial in X. And the coefficients of that polynomial are going to be denoted by C1 up to CP. Okay, so now we need, we're going to go back to this later, but now we need a little lemma. And this is a very kind of independent lemma. And this lemma is a statement about polynomial divisibility over, over finite fields. And it says the following. Suppose I have two polynomials. Let me call them capital R and capital S. And they all are polynomial. They're both polynomials in one variable x with coefficients in the finite field fp, where p is prime. And there are some conditions that they satisfy. The first condition is that they have constant term 1. So r of 0 and s of 0 is 1. And degree of r is at least 1. Okay, so we don't want r to be constant. So r is at least a linear polynomial. And then we have this condition that the GCD between r and r prime is 1. So r and its derivative does not share any factors. And r doesn't divide s. Okay. Now let m be any positive integer such that p doesn't divide m. Then the following condition holds. If you look at the polynomial rx raised to mth power times s of x, then you subtract 1, then that polynomial is not divisible by x to the power of degree of r plus degree of s plus 1. So certainly this statement is quite self-contained, but it's not so easy. We need to actually give a detailed proof. It's worth thinking about the constant term for a moment. If you look at this polynomial rx to the m minus sx, well, if you plug in x equals to 0, then you get the constant term. Well, if you plug in x equals to 0, you get r0 to the m times s of 0 minus 1. But r to the r0 by hypothesis is 1, because r of 0 and s of 0 are both 1. So if you plug in x equals to 0, you get the 1 minus 1, which gives you 0. This means that this polynomial has no constant term. What does that mean? That means that this polynomial is certainly divisible by x, because constant term is gone, so it's divisible by x. That's why it's interesting to ask, if it's divisible by x, you can ask, is it divisible by x squared? Is it divisible by x cubed? Is it divisible by x to the fourth? So you can ask, what is the highest power of x so that this polynomial is divisible by? And this result just says that it's not divisible by this power. So maybe there are other powers where this is divisible by, but this power here is already too big. It's already too big, so it's not divisible. So hopefully the statement of the lemma makes sense. And the proof is the following. So we're going to assume to the contrary that Rx to the m times s of x minus 1 is in fact divisible by this particular monomial, x to the power of degree of r plus degree of s plus 1. Then that means that I can write Rx to the m times s of x in the following format. It's 1 plus some polynomial times this particular monomial, x to the power of degree of r plus degree of s plus 1. And of course, p here is some polynomial with coefficients in fp. Now let's let k to be the degree of r, and let's let n to be the degree of s. Then let's take the derivatives of both sides of the previous equation. If I take the derivatives of the left-hand side, then I apply the product rule, and I get this term. And if I apply the derivative on the right, well, the derivative of 1 is 0, and the derivative of this can be calculated using the product rule. And that's why it's helpful to let k to be degree of r and n to be degree of s, because then this just becomes n k plus n plus 1. And so you see by the product rule that that's what you get on the right-hand side. But we also know that the constant term of rx times m to the rx raised to m minus 1 is 1, just because when you plug in x equals to 0, you get 1. Okay, so now let's take a look at this. This x to the power of k plus 1 must divide the left-hand side. Well, it cannot divide this term because that term has constant term 1. That means that x to the k plus n must divide the remaining term. So it divides this term. However, if you look at the degree of m times r prime x sx plus rx times sx, by definition, this is a degree at most k plus n minus 1, because degree of r is k and degree of s is n, and here you're taking at least one derivative. So the degree drops by 1. Okay, so how is that possible? Well, the only way a polynomial of degree k plus n can divide a polynomial of degree at most k plus n minus 1 is if the polynomial of degree k plus n minus n, this thing is 0 polynomial. Well, this forces this polynomial to be 0, but notice, if this is the 0 polynomial, then I know that r of x must divide this term, because r of x divides this term, so r of x must divide this term. But r and r prime are relatively prime, so r must divide m times s. But here we're going to use the fact that p doesn't divide m. This means that m is not 0 in the field fp. So how is it possible that r divides ms and m is not 0? Well, that means that r divides s, and that's a contradiction, because we assume that r doesn't divide s. Okay, so this completes the proof of the lemma. And now we can prove the theorem. So let P be a prime and let A and B be subsets of Fp of size at least 2. And suppose that the product of A times the size of A times size of B is less than P. Then this set of points, the Cartesian product A cross B, determines at least this many directions. So if you remember our setup, we actually specialized the product of hx and fx at the horizontal direction. That's when you plug in y equals to 0. And as we saw earlier, if you can show that C of C of y is not 0 for a small value of I, then the set will determine a lot of directions. So our goal is to show that some of these values, the value of Ci is not 0 for a small value of I. We want to show Ci is not 0 for some small value of I, because if you can show that, then that will show that A cross B determines P plus 1 minus I directions, which is what we want. We want to show that it determines a lot of directions. So our goal is to find a small value of I such that Ci is not 0. Let's let, again, K to be P minus Mn. And we assume to the contrary, we're going to assume to the contrary that the first K plus N minus 1 values are 0. So C1 and C2 all the way until C plus K plus N is equal to 0. We're going to actually reach a contradiction at the end, which will mean that one of these is not 0, which will be good for us. So for now, we're going to assume the first K plus N minus 1 coefficients here are in fact 0. We're going to let R of y to be the product of 1 minus bj times y, where j ranges from 1 to n. But notice that we had assumed that 0 is in B, and that means that one of these bj's is 0. So if you take the product, one of the terms in the product is going to be just 1. So that doesn't contribute to the degree. So the degree of R of y is not n, it's actually n minus 1, because you're missing that one factor. So this is important to keep in mind. And similarly, let's define S of y to be yk of f of y inverse, comma 0. And then S is a polynomial in y of degree at most k. What we're going to do is we're going to substitute x equals to y inverse into our equation. Then that will, and then we're going to multiply by y to the p. This is going to transform the left-hand side into this, right? That's because if you look at the definition of hxy, the Reday polynomial, if you plug in x equals to 0, if you plug in y equals to 0, you're just getting these terms. Because in the Reday polynomial, there was a term involving ai's, but those are gone. So you just get ry to the m. And if you plug in x equals to y inverse into x here, you get fy inverse of 0. And then you multiply by a high power of y to turn that into s of y. So this is just some algebra. Going from here to here is not that deep. But now, because we're assuming that C1 up to CK plus N minus 1 is 0, this means that if you look at this equation above, actually a lot of the terms drop out from the beginning. And, well, the 1 stays. And that means that this term can be written in the form 1 plus y to the power of k plus n times q of y for some q of y in fpy. And notice that the GCD between R and R prime is 1. This is because B has distinct elements. And if B has distinct elements, R has distinct roots, because the definition of R involved taking a product of elements of B, right? This was the definition of R. So if the BJs are different from each other, then of course this polynomial has distinct roots. And having distinct roots is known to be equivalent to the GCD between R and R prime being 1. And now we're going to say, let Q, and I'm using the notation of the original paper, but I'm realizing that maybe Q wasn't the best notation for the power, because earlier I used Q to denote the size of the field. But here the field that we only care about is FP. So FP is the finite field of order P. There's no FQ here in this discussion, so maybe it's okay. The authors use Q as the highest power of R that divides S. So then what we do is we take this equation and we rewrite it in this way. So if you look at this, there's nothing new here. This is exactly this equation. It's just rewritten in this way. Notice here that the powers R to the Q and R to the Q cancel. And here minus Q times n minus 1 and Q times n minus 1 cancel. So you, of course, get this. Now, of course, the advantage, I mean, this makes sense here because Q is the highest power of R that divides S. So that means S is divisible by R to the Q. So this is a legitimate polynomial right here in parentheses. This is not just a rational function. This is actually a polynomial. But now we're going to do some inequalities. So since R to the Q divides S, we have that sorry, I'm just missing a small equality sign here. So this is equality here, right here. So remember the degree of R was n minus 1. So degree of R to the Q is just Q times n minus 1. So Q times n minus 1 is at most is equal to degree of R to the Q, but R to the Q divides us. So that's at most the degree of S. And the degree of S was at most K. So what do we obtain from here? We obtain that K is bigger than or equal to Q times n minus 1. So K minus Q times n minus 1 is at least 0. And we have the following chain of inequalities. So let's take a look. So P minus Mn is K by definition. So because K is bigger than or equal to Q times n minus 1, that means that P minus Mn is also bigger than or equal to Q times n minus 1. That means that I can divide both sides by n minus 1. So that means Q is at most P divided by n minus 1 minus Mn divided by n minus 1. Then I consider the quantity M plus Q. So that is the same as M, which is this M, plus, well, I have an upper bound on Q. That's an upper bound on Q. So I get this as an upper bound. But if I look at M plus Mn, sorry, this is minus Mn divided by n minus 1 plus M, you can do the algebra to see that this is simply minus M divided by n minus 1. So in any case, it's strictly less than P. So what did we show? We showed that M plus Q is less than P. In particular, M is less than P. So P cannot divide M. On the other hand, Ry to the M times S of Y minus 1 is Y to the K plus N times Q of Y. So we have this follows from the previous equality because I saw that Ry to the M plus S of Y was 1 plus Y to the K plus N times Q of Y. So this was actually here. We're just rewriting it in the next slide. But if you look at degree of R plus degree of S plus 1, what do we get? Degree of R is at most n minus 1. Degree of S is at most K and plus 1. So this gives you this. That means the degree of R plus degree of S plus 1 is n plus K. But this means that this is y, not x. We don't have x here. This is just y. Y to the power of degree of R plus degree of S minus 1 divides Ry to the M minus S of Y minus 1. Right. This is just because of this identity here. if you look at what this says, this is saying that y to the power of k plus n divides ry to the m times s of y minus 1. And k plus n is at least as big as degree of r plus degree of s plus 1. And that means that y to this power, degree of r plus degree of s minus 1, certainly divides this polynomial. But this is a contradiction to our lemma. We had a lemma that says that this cannot happen, that this is too much of a power that cannot divide this quantity. That means that degree of r has to be 0, otherwise we have a contradiction, but then r of y is 1. And degree of r, but how is this possible? How can r of y be identically 1? Well, degree of r was n minus 1, so that would force n to be 1. And n was the cardinality of b, so b is equal to 1 in size, and that's a contradiction because I assumed that both a and b have at least 2 elements. So that's a contradiction. So what do we conclude? We conclude that in the expansion, of h of x0 times f of x0, in this expansion, at least one of c1, c2, all the way until c sub k plus n minus 1, one of these has to be non-zero. But then by the observation we made in the beginning, this means that the set determines at least p plus 1 minus the worst case scenario is if this is not 0, then we get that determines at least p plus 1 minus k plus n minus 1 directions. So that's the key. But if you look at what this is, if you just use some algebra, we get that this is p minus k minus n plus minus 2. But let's remember what k was. K was p minus mn. So this is p minus, in parentheses, p minus mn minus n minus 2. And p's cancel. And we get mn minus n minus 2. That means that the set A cross B determines at least mn minus n minus 2 directions. But there's nothing special about the set B. We can do a 90-degree rotation and get that A cross B also determines at least mn minus m minus 2 directions. Well, what we have shown, remember, m and n are the size of the sets A and B. And we've shown that A cross B determines at least this many directions and this many directions. So we've shown that the number of directions determined by A cross B is at least the size of A times the size of B minus the minimum of the size of A, the size of B, plus 2. And this completes the proof of the Di Benedetto, Solymosi, and White theorem. And then last 2 slides. Let S be a subset of FQ star. So this proves the Di Benedetto, Solymosi, White theorem. I just want to say one new result in the field, and this result is going to extend the results that we discussed to the case of more general graphs than just Paley graphs. And we have following definitions. So suppose S is a subset of FQ star with S equals to minus S, such that S divided by S is not FQ star. So here S divided by S simply stands for the set A divided by B, where A and B are in FQ star. So we're just saying that this set of all ratios is not all of FQ star. Then we consider the Cayley graph. So there should be no star here. This is just Cayley graph on FQ. So let me just get rid of this. So this is really Cayley graph plus. This is the additive group of the finite field with the connection sets being S. In the special case, when S is the set of squares, we obtain the Paley graph. But in general, this is not necessarily the Paley graph. And so the question is, what can we say about the clique number of these graphs? And well, it turns out that you can prove the trivial upper bound, and the proof is identical almost word for word to the proof that I showed in the very first lecture of this mini lecture series. And the trivial upper bound says the following: suppose you have a set S such that S is equal to minus S, such that S divided by S is not all of FQ star, then the clique number is at most root Q. This is the so-called trivial upper bound. And the proof is the same proof as I showed. So you let C to be any clique in this Cayley graph, and you let G to be any element such that G is not in S divided by S. This is possible because by assumption, S divided by S is not all of FQ star. Then we look at the map C cross C, C cross C to FQ, and this is defined by Vi comma Vj goes to Vi plus G times Vj. And we claim that this map is an injection. And this is an injection of sets. How do we prove that? Well, suppose Vi plus G times Vj is equal to Vk plus G times Vl. Then I can solve for G from this equation. And then I get that G is Vi minus Vk divided by Vl minus Vj. And if Vi is not Vk, then VL cannot also be Vj because it's this equality. But then if Vi is not Vk and VL is not Vj, then look at this difference. Both the numerator and denominator is difference of elements. And in C, but C is a clique, so the difference of Vi minus Vk actually lies in S. VL minus Vj also lies in S because C is a clique. That would mean that G is an S divided by S, which is a contradiction. So the only way to not get a contradiction is to get Vi is equal to Vk, and therefore Vj is equal to VL, assuming this. So we've shown that this map is injective, because if you assume that they have the same image, in fact, Vi must equal to Vk and Vj must equal to Vl. So the map is injective. So this map is injective, which means that the cardinality of the set on the left, which is cardinality of C square, is at most the cardinality of the set on the right. So it's at most Q. Now, if you take the square roots, you get that the size of C is at most root Q. And this is true for any clique. And because this is true for any clique, the clique number of X is at most root Q. So this is the proof of the trivial upper bound. And really, the proof really shows what's the only assumption that's necessary. And that's this assumption in the proof. S divided by S is not all of FQ star. This allowed us to pick G to be in FQ star, such that G is not in S mod S, and which allowed us to write down this map. And this is the last slide. So Chi Hoi Yip recently proved a far-reaching generalization of the Hanson-Petridis bound on the clique number of Paley graphs. So Hanson and Petridis proved the upper bound on the clique number of Paley graphs, and Chi Hoi Yip generalized this to arbitrary Cayley graphs of this type. And so here's what Chi Hoi proved. So let Q be an odd prime power of a prime P, and let S to be an element of is a subset of FQ star. So this is just a repetition here. Let S be an FQ star with S equals to minus S, such that S divided by S is not all of FQ star. Then what Chi Hoi showed is that the clique number of the Cayley graph on the connection set S is at most the size of S divided by S in the square root plus 1 if Q is equal to P. So if the size of the field is equal to the size of the prime subfield. And if Q is strictly larger than P, where P is the characteristic, of course, P is the characteristic of FQ, then you get a little bit of a worse bound. So then you know that the clique number is at most s divided by s, and the square root plus square root of q divided by p minus 1. Notice that in the case when you let s to be the set of quadratic residues, then s has q minus 1 over 2 elements. Then you get q minus 1 over 2. The s divided by s is again s because it's a multiplicative subgroup. And then you just get q over 2 here, which is exactly the square root of q over 2. That's exactly Hanson-Petridis bound. So this is an amazing achievement because it works for any Paley graph as long as the base graph is fq. So the vertex set comes from a finite field fq, and the connection set satisfies this condition. Now, this condition is natural because you want the set to be undirected. You want the graph to be undirected. And then this condition is a very mild restriction on S. And what's so interesting is that Chi Hoi's proof actually uses both methods. It uses both the Stepanov's method and the theory of directions, namely what we discussed today, the Sonyi's extension of Rede polynomials. All right, thank you very much for listening and for your attention.
Okay, thank you very much for the nice lecture and for the whole mini course. We have learned much today and previous days. I have a question. So as you said, this topic is very hot recently. Do you expect any further improvements of the Hanson-Petridis bound for Paley graphs?
Yeah, that's a great question. I have a feeling that there will be progress. I don't know if the original Paley graph will see progress. That seems very hard. But I think these graphs when S is a particular connection set other than the quadratic residues, I think there's much to be discovered here. And in particular, if you look at the case when S comes from the union of cyclotomic subfields. So the Chi Hoi has, you can specialize this to corollary in that case, and then you get upper bounds on the cyclotomic graphs. So there might be something there to investigate. And also here, there's this correction term. If Q is not P, you have this term. I'm not sure if this is also something that needs to be removed, for example. So you really would want to get something like this. And so my feeling is that it might be very hard to prove improve the Hanson-Petridis bound because it's about Paley graphs, and Paley graphs seems to be the most inflexible ones. But certainly improving the clique number of related graphs, that may be within the reach. And for example, there's the famous class of graphs that you are very familiar with, Pizer graphs, Pizer graphs. So Pizer graphs is definitely one avenue to look. And I think you can try to see if you can get better upper bounds of the clique number of those graphs, because I don't think they've been as thoroughly investigated as the Paley graphs. But yeah, I also wanted to point out for those who are listening is that Chi Hoi posted the latest version of his paper on the archive, version 3, in November 6, which is only a week before time I'm talking right now. So version 3 is a minor improvement, he writes in comments of version 2, which was posted in September. So this is very recent work. So whoever is interested in the field, you're encouraged to look into his paper and see if there are ways to improve certain results. But yeah, so this is quite nice, and so this might be interesting for people who are interested, who work in additive combinatorics, is to understand how big or how small can the set be? So if you take a set S such that S is minus S, this is not a large restriction. Look at the S divided by S. If you can make the set small, then that's really good. That means the clique number is tiny. So it might be interesting, and this is really a combinatorics, additive combinatorics thing, is how big or small is the set? If I give an arbitrary S, what can I say about the size of S divided by S? So I'm not sure if one can do some computer experiments, but this is already sort of interesting from that point of view. So maybe you can show that S divided by S is, so in the case of Paley graphs, S divided by S is P over 2, P minus 1 over 2, something like that, Q minus 1 over 2. But maybe if you take S to be a generic random subset, then maybe that is like tiny. So if you can maybe prove a probabilistic thing, maybe you can say, hey, S is randomly selected subset with this condition, then can I say something about the expected value of S divided by S? That might be very interesting to look at. And then that might tell you something about the behavior of a random Paley graph. So those are the initial things that pop up to my mind.
Yeah, very interesting. Thank you.
Thank you so much, Sergey.